All right. Our next speaker this morning is Swathya Singh Chauhan, who has joined us this year from UCLA. Swathya has been working this summer with Shengqi, and she'll tell us about their project together, an analytic model for nitrogen-2 emission lines from H2 regions.
Thank you, Gwen. I'm so excited to talk to everyone about the cool model that I've been working on this summer. So let's get started. First, I wanted to provide some background on H2 regions. So H2 regions are formed when high-energy photons from new stars ionize the nearby gas, which is primarily neutral hydrogen before. And we observe emission lines from these regions when the ions exhibit spontaneous decay, which is when the electrons within the ion go from a high-energy state to a low-energy state and photons are emitted. Looking at these emission lines from H2 regions is super important for a couple of things. Some of them include pinning down the redshift of the galaxies, tracing star formation within them, and also understanding the interstellar medium properties. For this talk, I'll specifically be focusing on emission lines and the interstellar medium properties. Some of the most commonly observed lines include H alpha, oxygen 3, carbon 2, nitrogen 2, sulfur 3, among many others. In the past, my mentor has worked on developing an analytical model for the O3 lines. So I'll be using her work and her concepts to extend the same model to nitrogen 2. In particular, we're really interested in nitrogen 2 lines because they've been detected in the data from the Atacama Large Millimeter Array for high redshift galaxies. And this is a line that's also of interest for upcoming projects, such as the Roman Space Telescope, which plans to observe this line at a low redshift. So if we can find a way to understand what causes these emission lines, we can infer the unobservable properties of the source, such as the gas metallicity, density, temperature, etc. And the best way to do that is through a model. In particular, me and my mentor are interested in developing an analytical model that is based on the underlying interstellar medium physics, and that will allow us to facilitate direct comparison between simulations and observations for testing as well as analysis. And the best thing about having an analytical model is that it can be much more computationally efficient in comparison to widely used spectral synthesis codes such as Cloudy or mappings. For the purpose of our project, we've been using Cloudy as for cross-checking and for computational efficiency comparisons. So these codes are very thorough and they account for a lot of different processes within the H2 region. And when calculating the line luminosities, we don't really need to be so detailed as these models run on a grid when post-processing simulations, which results in a lot of time being lost. So what we do is we strip down the process and narrow down on the key contributors to the line emission mechanism. And by taking this approach, we can actually speed up the computation time to almost 1,000 times faster. So here I have an example of my mentor's O3 model. And her model can be 1,000 times faster than Cloudy when post-processing fire simulations. So with the need for an analytical model discussed, I wanted to talk about how we go about analytically modeling these nitrogen 2 lines. So the key thing that we're looking at is what impacts the line luminosity. So we start off with a simplified picture of an H2 region. So we assume a spherical geometry, and we adopt a one-zone model, which means that we assume a uniform distribution of the gas properties, such as density, metallicity, and temperature. And we also consider a central ionizing source. So in this case, we have a central star. So the first thing we need to consider is the strength of the stellar radiation field that is being incident upon the gas around it, because this directly affects how much gas is being ionized and what kinds of elements, what kinds of ions you can see. Next, we need to account for the overall gas properties, such as the metallicity, specifically in terms of the nitrogen abundance in our case, because this is the nitrogen that will get ionized to nitrogen 2. We also account for gas temperature and gas density because they directly impact the collisions and the interactions that result in excitations, de-excitations, and decay. And finally, if you look at the figure, you'll notice that the N2 region is contained within the H2 region. And that is because the ionizing potential for hydrogen is much lower than the ionizing potential for nitrogen, for the first state of nitrogen. So that is why the N2 region will be smaller than the H2 region. And similarly, we can have N3 regions and 4 regions within the N2 region. And for our model, we only look at the N2 region because those are the ions that we're interested in. So we need to account for the volume of that N2 region as well. Besides the overall structure of the H2 region, we also need to consider the N2 ion itself, because ultimately that is the ion that will undergo the transitions that result in the emission lines. So for our model, we adopt a 5-level model for the nitrogen 2 ion. So in the figure over here, I have the bottom 5 energy levels of nitrogen 2. And I have a couple of transitions marked here. So the 122 micron and 204 micron transitions are ALMA targets, have been detected by ALMA. And then the others, the 5,000, roughly 5,000, 6,000 angstrom ones are JWST targets. And we are hoping they will also be detected in the upcoming papers. So we start off by calculating the electron population at the starting energy level for the transition, because ultimately this is the fraction that might undergo the transition that we want to take a look at. And we do that by accounting for the inflow and outflow of electrons at all of these 5 energy levels. Next, we combine that with the rate of spontaneous decay, because that is the probability of that transition happening. And combining that with the transition energy, we have a more quantitative number for how many ions are undergoing that transition. With all of these considerations in place, we can start taking a look at the equation that we use for our model. So I'm going to walk you through this equation. It has all the same stuff that I just mentioned. So the line luminosity for a transition from level I to J depends on the transition energy and the rate of spontaneous decay, which I just mentioned on the previous slide, and also the electron population at the starting energy level, which once again, we're calculating using the 5-level model. Next, it depends on the gas properties, such as the gas metallicity in terms of the nitrogen abundance, the gas density, the number of ionizing photons, which is a measure of the stellar radiation strength, as well as the volume fraction that the N2 region occupies within the whole H2 region. There's also the hidden parameter of the gas temperature here. Sorry, that's a slide error, but you see the temperature affects the alpha beta coefficient and also our calculations for electron population as well as the volume fraction. You just don't see it in this main equation. So with this equation, we can start making some plots. So for our results, I wanted to present some of our N2 line luminosity plots. So in this figure, I have the line luminosity for the 204 micron line on the y-axis, and then the number of ionizing photons on the x-axis. And both of the axes are logarithmic, so that we can see this a little better. And on this plot, we have the results from our model in solid, and then we're comparing our results to cloudy results, which are given in dashed. And we can see pretty good agreement between my model and cloudy, so that is a good thing. On the same plot, I also have the effect of increasing the number of ionizing photons, because with a stronger stellar radiation field, we expect more ionization, so the line luminosity increases. And I also have the effect of varying gas density. And so the different colored lines represent different densities, and with an increase in density, actually, so the density is increasing from up to down, there's a decrease in the line luminosity, and that is because collisional processes start to dominate over the de-excitation and spontaneous decay in this case. Similarly, we can see the effect of increasing metallicity. So I took the same plot, and it's in the center now. If you decrease metallicity, if you compare the lines, you see that it goes down. And if you increase metallicity, it goes up. And that is because the amount of nitrogen available to be ionized increases. And I also wanted to plot a a more zoomed in version of the differences between our model and cloudy results. So this is the fractional variation for the same set of parameters that you just saw in the previous slides. And our model is within plus or minus 10% of cloudy results for this commonly used set of ISM parameters, which is a really good thing because this means that we can start using this model and applying it to observations and simulations. So talking about observations and simulations, I want to list some of the things that we can do. So with observations, we can start making inferences about the unobservable properties in the currently observed data. We can use this model for line intensity mapping surveys, and we can also do survey forecasts for the upcoming Roman Space Telescope. As for simulations, we can start with post-processing fire simulations, and we can then compare the results with ALMA and JWST observations. So to summarize my work this summer, we have a complete N2 model, and it is in good agreement with cloudy results, and we're really happy about that. And next, we're working on applying the N2 model to fire simulations. And we're also developing a sulfur-3 model, which is currently in its preliminary stages because that's a similar ion and it also has great utility. And with that, I'm at the end of my presentation. Thank you so much.
Hi, excellent talk. Really, really interesting stuff. So you mentioned that your next steps are specifically to apply this model to the fire simulations. Do you think it would be difficult to adjust your model to post-process other types of simulations as well?
That's actually a great question. So we just finished the model very recently, like late last week. So I haven't had the chance to look at how we actually go about applying it to simulations. So I'm not super sure, but I believe it we should be able to adapt it to different simulations for post-processing.
Right. Thank
you.
Exciting stuff.
Thank you.
Hi, really interesting work. Thank you for that. I was wondering whether you include dust in your H2 regions, and if you do, what kind of dust?
Yeah, that's a great question. So this is something that I didn't mention, but I was hoping that I would get to mention. So our model right now does not account for dust because that would involve including more equations and like calculations. So our model at the moment is really good for high redshift galaxies because they're less dusty. But so that is why it can be easily applied to the ALMA high redshift data. But for the upcoming Roman Space Telescope, we're planning to do a survey forecast at low redshift. And for that, we plan to combine our model with other semi-analytical models or another model that accounts for dust. So yeah, not at the moment.
Oh, sorry.
Thank you. I just want to ask, like, what's the major difference in terms of mass and like background between like those different like N2 and S3 and like O3, I believe that you mentioned. What's like the main difference between building the models?
That's a great question. So I have a slide for that actually. Apologies for the complicated diagram. This is from the textbook Interstellar Medium Physics by Bruce Strain. So here I have the diagrams for the N2, O3, and S3 ion. And so the reason why, so the main thing here is both of O3 and N2 are 6 electrons. Sulfur-3 is 16 electrons, but then the shell structure starts coming into place. So that goes down to the orbitals basically, and all 3 of them have an nsp2 configuration, which makes them relatively similar. I'm still working on so O3 and N2 were very easy to work on together. I'm using the same equations. It's just the rates of decay and collisional excitation, de-excitation that change. Almost everything else is relatively the same when adapting O3 to N2. But for sulfur-3, I'm still taking a look at it. We're using the same approach, same equations. And based on our preliminary plots, results look good. So yeah.
All right, let's thank Swathya again for her.
Thank you.